Shielded cables are employed for current transformer, abbreviated CT, signals and breaker control signals to mitigate the impact of electromagnetic interference, abbreviated EMI, on these signals. Electromagnetic interference can originate from diverse sources, including other electrical devices, power transmission lines, and even lightning strikes. The shielded cable provides a conductive barrier around the conductors, thus safeguarding the signals from the disruptive effects of electromagnetic interference. Now, addressing the temperature rating of cables, 90 degrees Celsius rated cables are specified for 600 volts control cables due to their enhanced heat resistance compared to 75 degrees Celsius rated cables. This heightened heat resistance is crucial because control cables frequently traverse areas susceptible to elevated temperatures, such as proximity to motors or other equipment that generates heat. If 75 degrees Celsius rated cable were used in such environments, its reduced heat resistance could lead to damage. Regarding the National Electrical Code, abbreviated NEC, it does not mandate the exclusive use of 75 degrees Celsius rated cable for relay and breaker control signals. Instead, the selection of cable temperature rating must take into account the temperature ratings of the equipment termination points, specifically lugs and terminals. Should these termination points be rated for 75 degrees Celsius, then a 75 degrees Celsius rated cable is appropriate. Let's delve deeper into the reasons behind using shielded cables. Shielding provides a barrier against electromagnetic fields, preventing them from inducing unwanted currents or voltages in the signal conductors. This is especially important in control circuits where accuracy and reliability are paramount. These induced voltages, even if small, can cause malfunction of protective relays. There are different types of shielding. The most common types are braided shields, foil shields, and combination shields. Braided shields consist of woven strands of conductive material, offering excellent mechanical strength and good shielding effectiveness. Foil shields use a thin layer of conductive material, typically aluminum, providing good shielding effectiveness at high frequencies. Combination shields incorporate both braided and foil layers, offering the benefits of both types. The selection of shielding type depends on the specific application and the level of electromagnetic interference present. Now, regarding cable temperature ratings, the NEC specifies the allowable ampacities of conductors based on their temperature rating and the ambient temperature. The ampacity is the maximum current a conductor can carry continuously without exceeding its temperature rating. NEC Table 310.15.16 and NEC Table 310.15.17 provide ampacity values for different conductor types and insulation temperature ratings. For example, a 14 American wire gauge, abbreviated AWG, copper conductor with a 75 degrees Celsius insulation rating has a lower ampacity than the same conductor with a 90 degrees Celsius insulation rating. It's essential to select a cable with a temperature rating suitable for the intended application and the operating environment. Factors to consider include ambient temperature, proximity to heat sources, and the amount of current the cable will carry. Furthermore, the temperature rating of the cable must be compatible with the temperature ratings of the termination points. Using a cable with a higher temperature rating than the termination points will not increase the overall system temperature rating. The lowest rated component dictates the maximum operating temperature. In addition to temperature rating and shielding, other factors to consider when selecting control cables include voltage rating, conductor size, and insulation type. The voltage rating must be sufficient for the applied voltage. The conductor size must be adequate to carry the expected current. The insulation type must be suitable for the environmental conditions such as moisture, chemicals, and abrasion. In summary, shielded cables are used to protect control signals from electromagnetic interference. 90 degrees Celsius rated cables are preferred for 600 volts applications due to their enhanced heat resistance. The NEC does not mandate the exclusive use of 75 degrees Celsius rated cable for relay and breaker control signals, but the temperature ratings of the termination points must be considered. Selecting the appropriate cable for a specific application requires careful consideration of various factors, including shielding, temperature rating, voltage rating, conductor size, and insulation type. All this information will help ensure safe and reliable operation of electrical equipment. Let's further elaborate on the selection of shielded cables and the implications of using different shielding types. The effectiveness of a cable shield in reducing electromagnetic interference is quantified by its shielding effectiveness, typically expressed in decibels, abbreviated dB. A higher decibel value indicates better shielding performance. The shielding effectiveness of a cable depends on several factors, including the type of shielding material, the shield coverage, and the frequency of the electromagnetic interference. Braided shields offer good shielding effectiveness over a wide range of frequencies, while foil shields are most effective at higher frequencies. Combination shields provide a balance of shielding effectiveness across a broad frequency range. The shield coverage refers to the percentage of the conductor surface area that is covered by the shielding material. Higher shield coverage generally results in better shielding effectiveness. However, increasing shield coverage can also increase the cost and weight of the cable. When selecting a shielded cable, it's important to consider the frequency range of the expected electromagnetic interference and the required level of shielding effectiveness. For example, in environments with high levels of radio frequency interference, abbreviated RFI, a cable with a foil shield or combination shield may be necessary. In applications where mechanical strength is important, a cable with a braided shield may be preferred. The method of terminating the shield is also critical to its effectiveness. The shield must be properly grounded to provide a lower impedance path for the induced currents to flow. Improper grounding can significantly reduce the shielding effectiveness of the cable. There are several methods for grounding cable shields, including using shielded connectors, grounding clamps, and pigtails. The choice of grounding method depends on the specific application and the type of cable used. Shielded connectors provide a direct connection between the cable shield and the equipment grounding system. Grounding clamps are used to connect the cable shield to a ground bus or grounding electrode. Pigtails are short lengths of wire that are attached to the cable shield and then connected to a ground point. Now let's delve deeper into the implications of using 90°C rated cables versus 75°C rated cables. As previously mentioned, 90°C rated cables have a higher temperature rating than 75°C rated cables, which means they can withstand higher operating temperatures without degrading. This can be advantageous in several situations. Firstly, in high ambient temperature environments, using a 90°C rated cable can allow for a higher ampacity compared to a 75°C rated cable. This means that a smaller conductor size can be used to carry the same amount of current, which can save space and reduce cost. Secondly, in applications where the cable is exposed to heat generating equipment, such as motors or transformers, using a 90°C rated cable can provide a greater margin of safety. The high temperature rating allows the cable to operate at a high temperature without exceeding its insulation rating, which can prevent premature failure. Thirdly, using 90°C rated cables can simplify the design and installation process. Since they have a higher temperature rating, they can be used in a wider range of applications without having to worry about rating for temperature. However, it's important to note that using 90°C rated cables does not automatically increase the overall system temperature rating. The lowest rated component in the system dictates the maximum operating temperature. If the termination points are only rated for 75°C, then the system must be operated at or below that temperature, regardless of the cable temperature rating. Furthermore, the cost of 90°C rated cables is generally higher than that of 75°C rated cables. Therefore, it's important to weigh the benefits of using 90°C rated cables against the additional cost. In many cases, using 75°C rated cables may be sufficient, especially if the ambient temperature is low and the cable is not exposed to excessive heat. The NEC provides guidance on selecting the appropriate cable temperature rating for different applications. NEC Section 310.15 outlines the requirements for determining the ampacity of conductors, taking into account factors such as ambient temperature, number of conductors in a raceway, and type of insulation. NEC Table 310.15-16 and NEC Table 310.15-17 provide ampacity values for different conductor types and insulation temperature ratings. In addition to the NEC, other industry standards, such as those published by the Insulated Cable Engineers Association, abbreviated ISA, provide guidance on cable selection and installation. ISA standards cover a wide range of cable types and applications, including power cables, control cables, and communication cables. It's important to consult these standards when selecting and installing cables to ensure compliance with industry best practices. Now let's talk about some practical considerations for selecting shielded cables. When determining whether to use shielded cables, one must consider the electromagnetic environment. If the equipment is located near sources of electromagnetic interference, such as radio transmitters, motors, or power lines, then shielded cables are recommended. The level of shielding required depends on the severity of the electromagnetic interference. If the electromagnetic interference is relatively low, then a cable with a foil shield may be sufficient. If the electromagnetic interference is high, then a cable with a braided shield or a combination shield may be necessary. It is also important to consider the frequency of the electromagnetic interference. Foil shields are more effective at high frequencies, while braided shields are more effective at low frequencies. Consider the type of signal being carried by the cable. Signals that are sensitive to electromagnetic interference, such as analog signals or high-speed digital signals, should be carried in shielded cables. The length of the cable run also affects the need for shielding. Longer cable runs are more susceptible to electromagnetic interference. The cost of shielded cables is higher than the cost of unshielded cables. When deciding whether to use shielded cables, weigh the cost against the benefits of reduced electromagnetic interference. Consider the grounding requirements for shielded cables. Shielded cables must be properly grounded to be effective. Follow the manufacturer's instructions for grounding shielded cables. Consult with an electrical engineer or other qualified professional if you are unsure whether to use shielded cables or how to ground them properly. By considering these practical considerations, one can make an informed decision about whether to use shielded cables in a particular application. Now let's consider some common misconceptions about cable temperature ratings. One common misconception is that using a high temperature rated cable will automatically increase the ampacity of the circuit. This is not necessarily true. The ampacity of a circuit is determined by the lowest rated component in the circuit, including the cable, the connectors, and the equipment being powered. If the connectors or equipment are only rated for 75 degrees Celsius, then the circuit must be operated at or below that temperature, even if the cable is rated for 90 degrees Celsius. Another common misconception is that using a high temperature rated cable will improve the reliability of the circuits. While it is true that high temperature rated cables are generally more resistant to heat and degradation, they are not immune to failure. Other factors, such as mechanical stress, chemical exposure, and moisture, can also cause cable failure. The key is to follow proper installation procedures. Also, make sure that you are using the right cable type for the installation. And it is important to inspect the cable regularly for signs of damage or degradation. Another misconception is that the NEC requires the use of 75 degrees Celsius rated cables for all circuits. As mentioned earlier, the NEC does not mandate the exclusive use of 75 degrees Celsius rated cables for relay and breaker control signals. The NEC allows the use of high temperature rated cables, provided that the termination points are also rated for the high temperature. The final misconception is that using a lower temperature rated cable will save money. While it is true that lower temperature rated cables are generally less expensive than higher temperature rated cables, using the wrong cable can be a costly mistake. If a cable is not rated for the temperature at which it will be operating, it can overheat and fail, leading to equipment damage, fire, or even injury. When selecting cables, it is important to consider the temperature rating, the voltage rating, the current carrying capacity, and the environmental conditions. Select a cable that is appropriate for the application. Consulting with an electrical engineer or other qualified professional can help ensure that the correct cables are selected and installed.